I'm Molly. Like Jamie, I also work with Seth Stein. And today I'm going to be talking about the work I've kind of been doing over sort of the last year and the past summer, which mainly focuses on looking at how site effects affect seismic hazard map performance relative to historical data. So for those of you who do or don't know, I guess, this work is kind of stemming off of the work that Leah Saldich did with the California Historical Mapping and Historical Intensity Mapping Project, or CHIMP is the acronym for that. So that's the figure all the way on the left here. We collected a data set of the shaking from the largest earthquakes in California over the past 162 years. And we've used that data to assess seismic hazard map performance. So far, preliminary or work that Leah did showed that the seismic hazard maps appear to overpredict shaking relative to the CHIMP data set. And so now I'm looking at whether an aspect of the hazard calculation, specifically in the ground motion models, might be contributing to that overprediction. So what I'm looking at is whether the site-specific VS30 parameter, VS30 is the shear wave velocity in the top 30 meters of soil, whether incorporating this parameter might affect the hazard maps. So this plot all the way on the right shows how VS30 affects or amplifies or de-amplifies shaking relative to the 760 meters per second. That's currently the standard used in USGS seismic hazard maps. So overall, what we see is that at low VS30s and low levels of shaking, we would observe linear amplification. And then as the shaking increases, as the shaking level gets stronger and still at that low VS30, we would actually see de-amplification due to nonlinear effects that come from soil damping. So when we site correct the hazard maps for the site-specific VS30, we find that there's really no difference. There's very, very minor differences, as you can see in the residual map here. And mostly the site-specific hazard map is slightly higher than the original. And these small differences are due to the nonlinear de-amplification, offsetting linear amplifications at short periods relative to NMI. And at longer periods, site effects are larger because that nonlinear effect goes away at longer periods. I'm also just getting started on, and this is something I was working on over the summer, on running hazard models for France, which has been interesting. It's mostly done in, the program is all in Fortran, which has been a learning curve because I haven't used that before. So it looks a lot like this, but we've been making fault models using various previously published things, and I'm using the Quest supercomputer cluster. So I get a lot of runs that look like this where they fail, but we're making progress, and that'll hopefully be something that we can do to look at individual hazard curves, to look at the median versus the mean hazard, and then apply that to California in the future.